So the Fermi level is constant in equilibrium, a statement we have come across in various device physics textbooks or courses. But have you ever wondered why this statement is true? So in this video, I'll be breaking down the reasoning behind this fundamental concept and how it actually connects to the equilibrium conditions in a semiconductor. So welcome back to part 2 of the series on energy band diagrams. So firstly, let's try to understand what this Fermi energy level means. So this actually comes from the Fermi Dirac statistics, and this gives the balance between the electron and hole concentration in the material. So what I mean is, suppose you have your Fermi level at the center of the band gap. This means that the probability of finding the electron in the conduction band is equal to the probability of finding a hole in the valence band. So this essentially means that the concentration of electrons and holes are equal in this material. So as this Fermi level moves closer to the conduction band, then this probability of finding the electron actually increases compared to that of holes, which means that the concentration of electrons is greater than that of holes. On the other hand, if the Fermi level actually moves closer to the valence band, it means that the probability of finding holes is increasing, which means that the concentration of holes is greater than that of the electrons. Alright, so this is the information regarding the probabilities and carrier concentrations. So the Fermi level is also like a reference energy level for electrons in the material. So what I mean is, suppose you have two materials with different Fermi levels. So this is material A and this is material B, and suppose the Fermi level of material A is higher than that of the Fermi level of material B. So we actually tell that the chemical potential of A is actually greater than that of the chemical potential of B. So what this means is the number of electrons that is there in the conduction band of material A is actually greater than the number of electrons that is there in the conduction band of material B. So to give a simple analogy of what this means, so suppose you have two buckets that has different level of water. So the level of water is actually analogous to the Fermi level that we use in solids. So now let's try to understand why the Fermi level is actually constant in equilibrium. So before that, let's understand what this equilibrium is. So what it means is that the net flow of charge is equal to 0, which implies that the current is 0. And the next thing is the net transfer of energy is equal to 0, which implies that there is no applied voltage or heat or any illumination on the device. Alright, and just few more basics. First one is the density of states. So what it tells is the number of quantum states available for a given energy level. And next is the Fermi function, which gives the probability that the state is occupied for the given energy, and which also implies that 1 minus f of e is equal to the probability of the state being unoccupied. So to give a simple analogy of this density of states and Fermi function, so you can assume that you have a movie theater where the price of the ticket is actually the energy level. So ticket price is energy level, and the number of seats in the theater is actually the density of states. Number of seats is actually the density of states, and the probability of that states being occupied is actually the Fermi function. Alright, and also the concentration of electron is actually proportional to the product of the density of states and the Fermi function. So with this in background, let's take an example and see why the Fermi level is actually constant in equilibrium. So suppose I have two materials with different Fermi levels. So this is material A and this is material B. So from the previous discussion, we know that the number of electrons in the conduction band of A is actually greater than the number of electrons in conduction band of material B. So this implies that there is a concentration difference between the electrons in material A and material B. So what happens due to this concentration difference? Electrons flows from material A to material B. So as this electron flows, there is buildup of these negative charges in material B, and since there is loss of electrons, there is a build of positive charges in material A, and this actually gives rise to a built-in potential, and as this potential builds up, it actually stops any electrons flowing from A to B. So this flow is actually reduced, and also there is this drift component, that is there is electric field that is built up in this direction, so which implies that the electrons will be pushed from B to A. In equilibrium, the number of electrons that is moving from A to B will be equal to the number of electrons moving from B to A. So let's try to calculate what this number of electrons that is moving from A to B is. So for A, so from material A to B, so let's say the density of states for A is given by SA, and the Fermi function is given by Fe. Alright, and this is the number of electrons that is there in material A, and we have to find what is the number of vacant spots that is there in B, and that is given by the density of states of B into 1 minus the Fermi function of B, and times some constant is equal to the number of electrons flowing from A to B. Similarly, the number of electrons flowing from B to A is given by the density of states of B and the Fermi function of B and the number of empty states that is available in A, which is given by this. So in equilibrium, these two should be equal. So equating these two, we can easily find that f of A is equal to f of B, which implies that the Fermi energy level of A is equal to the Fermi energy level of B. So this tells that in equilibrium, the Fermi level actually aligns, that is, the Fermi level is constant in equilibrium. So to give a simple analogy of what is happening, so suppose you have two buckets with different level of water, and now what I do is I just connect these two buckets. So after some time we notice that the level of water in both the buckets are equal. So this is the same thing that is happening in devices. So suppose you have two devices with different Fermi levels and you join them, and at the equilibrium, Fermi level aligns and becomes a constant, and the same thing is happening even in this example as well. Alright, the Fermi level is constant in equilibrium, and this is a very important fundamental concept when you are trying to analyze energy band diagrams, because when you just look at energy band diagrams and you see that the Fermi level is constant, you can easily tell that the device is in equilibrium, which actually implies that the current in the device is zero. And one more important thing is the Fermi level actually sets the starting point for drawing energy band diagrams in equilibrium condition. So I'll give more details of this in the future videos. So that's it for this video, and thanks for watching.